we start with MATLAB programming with state space. The meaning is that whatever we have studied earlier, particularly modeling, stability analysis, state transition matrix, state equations. So, if we are having a software, then how to determine this using a software? Now, a software we have to use, that is MATLAB, because MATLAB is very important tool which can helps us in the analysis of the system. Now, here we are going to study modeling of state space, second one is stability, then performance analysis and state transition matrix. Now, modeling of state space, I think in classical control we have seen a transfer function, that is g of s, which has been represented by numerator by denominator. But now here is the model which has been represented in terms of x dot equal to ax plus bu and y equal to cx plus du. Suppose we know a, b, c and d, and we have to replace, or we have to put all these a, b, c, d in a MATLAB file. So, what we can do? We can write a command a, b, c and d with ss. Ss means state space. The procedure is, if you go to the MATLAB window, you have to write a elements, say a equal to 1, 2, 3, 4. Then we have to write b elements, say 1, 0, then c 1, 0 and say d equal to say 0. So, here a, b, c, d, and if you and afterward you have to write this command, you will get a, b, c, d directly. Now, about the transfer function. Transfer function, as I have seen, g of s equal to numerator by denominator. Suppose we have transfer function 1 divided by s plus 1, this is simple transfer function, and this we have to write in a MATLAB. So, in that case you have to write a command, say numerator num 1, and now we have to write denominator den. Now, here s plus 1 we write 1 1, and finally the complete system transfer function, that is sys tfm, that is transfer function model equal to tf. So, this is the command tf. Now, this numerator and in denominator will get a transfer function like this using a MATLAB. Now, another part, transfer function to state space. We have seen earlier that if you are having a transfer function model, we can easily convert it into companion form, canonical form, including diagonal form, Jordan form. Now, what we want to convert a given transfer function into a state space. So, see here, this is GS, this is transfer function model, and this is a state space. This is transfer function, and now this is a state space SS model. What we want? Transfer function to state space. So, we start with writing command tf, this transfer function to, and ss, tf to ss, that means we are getting a state space model. And what is the input in this case? Input is numerator and denominator. So, we will get a, b, c, d. That means from a given transfer function we can easily determine A matrix, B matrix, C matrix and D matrix of a state space model. Now, another part, state space to transfer function. Now, this is state space model. Now, here is the transfer function. We have seen various algorithms for determining transfer function from a given state space model. That is, if you want to do it by manual calculations, so what we can write C Si minus A inverse B plus D. This is a transfer function, that is say G of S, or we can use a level algorithm. But the same thing, if you required in a MATLAB, the command which we have to use, that is SS to TF, just here SS to TF, that is state space to transfer function, and here we will get output in terms of transfer function. Therefore, here we have entered A, B, C and D. Now, we take another example. Now, we take the example as G of S equal to S plus 1 divided by S square plus 2S plus 1. Now, this is a transfer function model. Now, first of all, what we want, this transfer function we have to write in a MATLAB, in MATLAB environment. So, this S plus 1, this indicate numerator, and this S square plus 2S plus 1 indicate denominator, numerator and denominator. So, numerator we can write down in MATLAB NUM, then this S indicate 1 and this 1. So, this is numerator. Now, about the denominator DEN, that is equal to 1, 2, 1. So, numerator we have entered, denominator we have entered, and as I discussed, this is SYS transfer function model, that is equal to TF numerator comma denominator. This gives you in MATLAB the state space model as S plus 1 S square plus 2S plus 1. Now, we have got a transfer function model. Now, what we want, these transfer functions we have to convert into a state space model, that is the transfer function which is got by MATLAB. By MATLAB we get transfer function model as S plus 1 S square plus 2S plus 1. This model we have to convert into a state space form. Now, as we have seen the command which we can use here TF2SS. So, here we can write down a command as A comma B C D, that is TF to SS numerator NUM, denominator. So, if you use this command, the result which will obtain using MATLAB, that is A matrix as A model, that is -2 -1 1 0, then B model 1 0 and C model 1 1 and D model as 0. So, here by means of this command TF2SS we have got a state space model like this. But here if you see the model, this model is of say a different form A, B, C, D, but if you do it manually we can write down this model as A equal to 0 1 -1 -2, B matrix as 0 1, C matrix as 1 1 and D matrix, this is 0. That means using MATLAB you got this result, but you can also get result by this way manually, but if you determine the eigenvalues of this, you will get the same values. That means property cannot change if you convert given transfer function model into a state space model. So, you will find that this A, AM, BM, CM, DM, here A, B, C, D both are the same thing, properties remain same. Now, about the multi input multi output system, because in practice system is generally of multi input multi output form, then in that case how to determine the model, that is how to determine the transfer function model from the given state space model. So, the command which we have to use, that is numerator denominator, this is SS, this is state space to transfer function A, B, C, D and U. IU means particularly input, that means which input you are taking. Let us say 2 input, so here 1 for first instance, for second instance we will get 2. That means this command for 2 input system can be written as numerator denominator SS to TF A comma B comma C comma D input 1. Input 1 for 2 input system we have written input 1. Then for second input numerator denominator SS to TF A comma B comma C comma D comma 2. So, these are the commands for 2 input system. Now, how to use this command? I will take the example. So, example, this is for 2 input 2 output system, and we will see in what way we will get the result using MATLAB. Now, here x1 dot x2 dot 0 1 minus 1 minus 2 x1 x2 plus 1 1 0 1 u1 u2. Now, this is state model. You will see that there are 2 inputs. Now, about the output, output is y1 y2 1 0 0 1 x1 x2 plus 0 0 0 0 u1 u2. So, you will find that this is a 2 input 2 output system, and the most important point you will see that whatever may be the multi input multi output system, but if you see the order of the state space model, 2 row 1 column, always column is 1. If there are n states, it will be n cross 1, and this will change, but state model or state equations, particularly states, remains same. It is always a first order. That is the advantage of the state space model. Now, this state space model we have to write in a MATLAB environment. So, how to write down? So, as discussed earlier, this command we have to use. So, here we can write down numerator NUM, DEN denominator, SS to TF, A comma B comma C comma D comma 1. Now, so if you write this command in a MATLAB, we will get a result, and you will find that the result will get numerator you will get as 0 1 2, 0 0 minus 1, and denominator will get 1 2 1. Now, here we have got numerator 0 1 2, 0 0 minus 1, and denominator 1 2 1 when you have input 1, input as 1. Now, here when you use the command numerator, denominator as SS to TF, A comma B comma C comma D comma 2. Now, here we are applying the input 2, and therefore, we will get the numerator as 0 1 3, 0 1 minus 1, and denominator will get as 1 2 1. So, here we will find that there are 2 inputs and 2 output system. So, here outputs are y1 y2 and inputs are u1 and u2. u1 u2 are the input, y1 y2 are the output. So, here we will get 4 transfer functions. The first transfer function, because of the input u1 of s, so here we can write the first transfer function y1 of s of u1 of s, we use just here 1 2. So, we can write s plus 2 divided by the denominator s square plus 2s plus 1, s square plus 2s plus 1. So, here input u1 is applied, that time output is y1. Similarly, output is y2 of s, and when same input u1 of s, we can write down this as minus 1 divided by s square plus 2s plus 1. Now, coming to this part, here your input is 2. So, output y1 of s, because of input u2 of s, this is 1 3, that is s plus 3 divided by s square plus 2s plus 1. Similarly, output y2 of s, because of input u2 of s, we can write s minus 1 s square plus 2s plus 1. So, these are the 4 transfer function we can obtain by using MATLAB, and here we have to use the command TF. TF of numerator and denominator will get 4 transfer functions. So, it means that even though our state space model involves multi input multi output system, we can easily determine the transfer function models. Now, about the canonical state space representation. In earlier part, we have seen different type of transformation, that is controllable canonical form, then controllable observable form, then we have seen a diagonal form, Jordan form, different types of forms we have seen. So, this type of form can be possible to determine using MATLAB. So, there is one command is available in the MATLAB, that is, if you write the command CSYS canon SYS type, this gives you the information about the diagonal form as well as the canonical form, that is controllable canonical form, or we also call as comparison form. So, here this is type. So, if you want diagonal canonical form, that is, if you want the A matrix involves diagonal elements, so in that case here we can write the command as CSYS canon SYS, and we write the command as a model here that gives you the diagonal canonical form. But if you required that this given system we have to represent in a comparison form or a controllable canonical form, we have to write the command as CSYS canon SYS, and this we can write. So, we can get the different types of state space representation, and we have already seen that transfer function is unique, but there are different types of state space model can be determined. It means that the eigenvalues of given matrix A can never be changed, whatever be the transformation we can use. Now, we solve an example. Suppose SYS equal to S plus 1 divided by S square plus 5S plus 6. Now, this system we have to represent in a diagonal form using MATLAB. So, the command which we can use CSYS canon CANON SYS comma model So, if you write the command CSYS canon SYS model, and you can get the result as a matrix as -3 0 0 -2, we will get B matrix as -3.606 -2.828 and C matrix -0.5547 0.3556 and D matrix is 0. That means we will get A, B, C, D, that is in particularly the given system, it is in diagonal form. You will see that for this S square plus 5S plus 6, there are two eigenvalues, one is -2 and another is -3. You will find that they will come in a diagonal form if you use this particular command. Now, we want this system in a companion form. The command which you can use CSYS canon CANON SYS, and here command is companion. So, if you use this command, you will get the result again in terms of ABCD matrix. So, here we will get result A matrix as 0 -6 1 -5, B matrix as 1 0, C matrix as 1 -4 and D matrix as 0. So, here if you using this command, if you got A, B, C, D matrix and A has formed 0 -6 1 -5, but I think we will find that this is somewhat different than we have determined the companion form. That is, if you go through the actual model and if you manually determine the companion form or we call as controllable canonical form, you will get A matrix as 0 1 -6 -5, B matrix as 0 1, C matrix as 1 1 and D matrix equal to 0. So, here we will find that if you make the transpose of this, you will get this part. So, this is also a one type of a companion form, and we will find that all these three forms have the same properties. So, sometimes whenever we come across a requirement of the forms, we can use this type of form, and most important is that all this form we can use using MATLAB, we can get it, there is no need for any calculation. We will find that as the order of the system increases, to convert one form to another is quite difficult, but luckily we have MATLAB software we can use for the analysis of the systems. But in that case, the important thing is that we want some variable, because whenever variables are there, we can easily carry out all these type of things. Now, the stability in a state space model, this is a very important point, and we have seen how to determine the stability of a given state space model. When we have seen the stability, we have seen how to determine the stability of a transfer function model. That is, if g of s is there, numerator by denominator say s plus 1 upon s square plus 2s plus 1. This is your transfer function model. If you want to determine the stability of this model s square plus 2s plus 1, so how do you determine? We can write the command as m equal to roots 1 2 1 bracket complete. Here we will get roots, as this is second, you can say we have a second order model, we will get m1 and m2, and based on this m1 and m2 we can decide the stability of this model, particularly this model is it in open loop model. But now we want to determine the stability of the system in a state space model. The state space model is x dot equal to ax plus bu, y equal to cx plus du, and we have seen that the stability of this state space model, it depends upon the A, and we have proved that y stability of a system in a state space model A is same as this denominator. But now if you want to use the MATLAB, we have to use the command eigen. Eigen of A, if you use this command, you will get the eigenvalues of matrix A, and if the eigenvalues of this matrix A lying on the left hand side, then we call the system as a stable system. But if you use this command, if you get any one of the eigenvalue on the right hand side on the S plane, we get system is unstable. So that means stability we are getting by means of a simple eigen command, whereas in case of transfer function approach we can use the command as roots, we can get the stability of the system. Now the response in the state space model. In a classical control, normally we are using a simple step command or sometimes impulse command to get the response of the system. That means we have seen that if you take a transfer function as numerator by 1 and denominator as say 1 to 1, so how you do it? Sys equal to transfer function numerator denominator. So this is a transfer function, and simply we are writing down the command step sys, that gives you the step response of the system. Suppose if you want impulse, we can get the response of the system, particularly in transfer function form. So this type of step command as well as impulse command we can also use in a state space model. But sometimes we cannot define our inputs. Input can be any arbitrary, or we can have any arbitrary inputs. So in that case, how to determine the response of the system using MATLAB, and this is every time required. It is because we have a state space model, then in the state space model different inputs will come, sometimes disturbance will come, so the disturbance may have different nature, therefore your inputs will also change, therefore this step command cannot be used every time. So therefore if you see the MATLAB literature, there are various commands have been available which can help us to get the response of a system. So here these are the commands are step response, impulse is impulse response, then this is the initial command, that is response of state space system to the given initial state, and LSIM, this command is called LSIM, this is for response to any arbitrary inputs. Now using any example you can see how to determine the response of a system when any arbitrary input is given. Now your system is represented by say matrix A is 0 1 minus 6 minus 5, this is A matrix, B matrix as 0 1, C matrix as 1 1, and D matrix is 0. Now, here we want to determine the response of a system for any arbitrary input. Now, first of all we will see how to determine the response of this system, let us say step input. As step input normally we are using for transfer function model, but we will find that for this model also we can use the step command to get the response. So, here what we can do, we can write say sys equal to ss state space, we can write down a comma b comma c comma d, then we can write the command as step sys that gives you the step response of the system. Now, our main purpose is to use then any arbitrary input, and as I discussed earlier, we can use the command lsim. Now, how to use it? So, here we can write for lsim how to use lsim command. So, here sys equal to ss a comma b comma c comma d, then we have to define some initial conditions. See, initial condition can be defined as a 1 1. Let us say we define a time as say 0, 0.01, 1. Then input, this is the input u. You can take any input. Now, here I can take say 0, say multiplied by say t. You can take sin t, cos t, any you can take, but it has been represented with time t. So, u 0 into t, and here y comma t comma x, we can write on a lsim sys, here input u time t, and here is the, we can say x naught is the initial condition. So, this command we can use. And now we want the state response. So, here we can write down in the way, because here we have two states, there are two states. So, we can write one figure 1 plot t comma x 1 that gives the response for state 1. Similarly, we can write down figure 2, and we can write the command as plot t x now. This gives you the response of the system because of the different states. If you want output response, we can write the command output y with respect to time t. So, in this way we can get the response of states as well as the output. But now here we have got response in two different figures. Now, here if you use the MATLAB, first of all one window will come, this shows figure 1, and afterward we will get figure 2 as another window. So, two different windows will get, and we can get the result, but sometimes what we want result in a one particular window like this. If you want, this is a one particular window and we want result like this, the first result should be like this one, and second result should be like this. So, in that case we can use the command as subplot. So, if you write the command like this, subplot, now here 1 indicate 1 row, 2 column, first this is the first row like this. Now, here 2 means 2 column, and here is the first positions. So, if you write this command subplot, and after that if you write this, you will get the result, this will printed here. That means this result, if you there, it will printed here, and if you want another result, subplot 1 comma 2 means 1 row, second column, and the second position, and again if you write this command, you will get the result of this here. That means the results we can plot in any of the window, or the same window or a different window. Similarly, we can also get result in this, like this window, this position by means of this subplot command. Even we can use also hold on command. If you use the hold on command on the same window, we can get the two results. But sometimes if you want a better understanding of the system, we can go for this results, this response or this response. I think this is far better, because the same result we are getting in a one particular window. Now about the state transition matrix, that is e raised to at. We have seen the different methods to get the state transition matrix. We have seen a power series method, then we have seen the Laplace transform approach, we have seen diagonalization method, and also we have seen Cayley-Hamilton theorem. And aim of all this method is to get the state transition matrix. But again you have seen calculation wise is quite difficult. If you increase the order, it is quite difficult. Therefore, we have MATLAB, which within a single command you can get the state transition matrix. But here main thing is that this is the point t. If you want the result with respect to time t, which is in generalized form, we can write the command SYMST, and this is STM EXPM like this. A multiplied by t, A star t, if you use this command, you will get this directly a state transition matrix A into t. That means whatever is the matrix, that is like x dot equals to say Ax. Now this is A, we can let us say write down in terms of A, where A equals to small a equals to capital A. If you write like this, if you write A star t, we will get the state transition matrix. So here we have seen all the MATLAB commands which can be helpful to get the state transition matrix, then response, different types of modeling. So this studies, whatever we have studied, that is the first part of the MATLAB. Now we will go for the second part of the MATLAB, when we will study the concept of controllability, concept of observability, then controller design, include pole placement design, observer design. So that part, that in that case we will go for the part 2, and we will see again how this command helpful in that case. Now some references, we can use these references and try to solve as many example as possible using these commands. Thank you.